CD8 is killer cell, CD4 is helper cell, CD3 covers both CD4 and CD8, and monocyte is a precursor of macrophage, NK is a natural killer. Wow. MHC is an antigen presenting molecule, and that pairs CD4 MHC2, CD8 MHC1, 2 multiplied by 4, 8, 1 multiplied by 8, 8. Not correctly also. MHC2 is a partner of CD4, MHC1 partner with the CD8. CD is a cluster of designation or cluster of differentiation. Those are usually proteins which represent different cells, not necessarily, but some proteins were chosen for discriminating different type of cells, and those are the CD. Okay. The total number of our gene is about 25,000, and if you include post-translational modification, acetylation, glycosylation, phosphorylation, those diversity may be much bigger, maybe almost million. Different kinds of proteins can be expressed. Among them, some proteins were selected, which shows some different expression on cell surface. Immunologists have a meeting every several years, and then they try to share their experience of working with those series, which one is working best, and which company's product is the best, kind of a communication they do. And then also the recent one is they suggested 371 as recommendable with a company and batch number together. If you buy the antibody from that company, most likely it will work. So compared to the total number of our gene product, 25,000, 371 is relatively quite small. It's not a little more than 1%. Maybe because this was only cell surface, means without killing the cell, antibody cannot penetrate the cell membrane. Without killing the cell in live status, whether the antibody can recognize the cell or not. Those cells are collected as a CD. Only 371 so far. Cancer cell has their own antigens. They don't want, but it's pushed to express those antigens on the cell surface by binding to MHC. So I don't want to present my antigen. I don't want to use MHC. Then what happens? If they don't use MHC expression, then NK cells check, and then you don't have MHC, then kill it. That's kind of a complementary effect mechanism. 보시는 사람들 보겠어요. Antibody is made by B cells, and helper cell, killer cell, helper cells, they help to make more antibody maybe, but production itself of antibody is done by B cell. NK does not make anything. Okay. Today is initial point. The theorem is going to present. And look at here. There is a PD1 and PDL1 as an example. PD1 sounds like the receptor. PDL1, PD ligand 1 is this. How do you define which one is the PD, which one is the receptor, and which one is the ligand? How do you distinguish receptor and ligand? Sometimes the definition of a biological stuff a little silly. Any suggestion? Idea? Suyon? 나중에 썼는데 아니네. 또 정훈아?
I think the objection in system is heterosexual. I think the gun should be cells.
Actually, is that true? Opposite. Cancer cell present PD-L1, T cell present PD-1. Okay, that's a good try, but it's not. Then what do you think? How do you define which one is receptor, which one is ligand? You may say receptor if it binds may change conformation of something, it ligand it. Then how will you define?
Our body's molecule is not as receptor.
That's one nice try. If it's not peptide, then maybe the ligand can be small molecule or carbohydrate. It's possible, but in this case, both of them are peptide. One is a protein, a little bigger one we call protein, small one we call peptide. I gave you the answer.
Here one is receptor.
눈치 빨라. That's a little silly, but yeah, bigger one we just pick up as a receptor. Small one as a ligand. Sometimes it's a dimerase, then ligand receptor is the same. So that's just by definition. But more important, the discrimination. How do you define which one is receptor and which one is the enzyme? For the signal transduction on the cell surface, sometimes there is a receptor, but sometimes the receptor itself is an enzyme. How do you distinguish receptor from enzyme? Active site. Receptor has also the binding site. Maybe we assume the binding site is active site. Second, change of conformation change. conformation can be changed for both of them. Enzyme also can work as an induced fit. Binding and changing conformation is possible. The change is good start. Energy state change is also conformationally changed means most likely it's energetically more stable direction changes, right? So it may not be more critical point or critical difference. Change is a good clue.
Substrate
Substrate.
change.
Substrate is a change, then we call it enzyme. Substrate is a change and it forms product. That's enzyme. Ligand, even though it binds, ligand does not change. Okay? If the ligand is a change, then we call that as enzyme and substrate. Okay? So that's a good definition. Yeah, CAR-T has a T-cell receptor, maybe or maybe not. If the cell has a T-cell receptor, it's a T-cell. Okay? If the cell has a B-cell receptor, that's B-cell. If it is an NK receptor, that's NK cells. But this is a CAR-T. Chimera of antigen, chimera of CAR. 그게 chimeric antigen receptor, T cells. It is engineered to have that artificial receptor, which is antibody fragment. So, to make the CAR-T, you can remove T cell receptor or just let it be, so that's optional. But technically, you should have antibody motif. That is the key concept of CAR-T. So, all the details you will hear from Daeun. Single chain free. Single chain fragment free. Antibody, this part. Okay, so we will see the structure. Okay, today we are studying the third topic of anti-cancer treatment, so-called immunotherapy. Okay, so immunotherapy, somehow we use immune system. Immune system, first of all, among our blood cells. In our blood cells, most abundant cell is erythrocyte or red blood cell, which does not have a nucleus, and they carry oxygen, and they compose 70% of all of the cells. 70%, a lot, right? That's very small and highly dense in blood. So these are just the functional of the oxygen carrier. Other than that, we have white blood cells. Those white blood cells, this is macrophage, so-called phagocyte, and when they are circulating in the blood, it's called as a monocyte, small round shape. When they have a signal, either infection of a bacteria or there's some cancer, then from blood stream, they penetrate out through the blood vessel and go into the tissue. And then differentiate into the umbrella shape. That is what we call the macrophage. The macrophage, monocyte, same. And these cells are kind of non-specific attackers. If the cell's target looks strange, then check it and kill it. Usually chemically. Now, these guys, granulocyte. So these guys usually, let's say, they usually gun, kill one by one. And these granulocytes, they carry grenade, bombs. So these vesicles are all bombs. And then they meet something, they just put those grenade explosive. So that means they can generate a lot of electro damages here and there. Create a lot of those damages. So these are usually the first line defense, like the Clemo explosion, and they live only 2-3 days. Macrophage, they live several weeks. Means they are little more specific. Now, these are, they don't use any antigen recognition. They just check whether these are normal or not. Me or invaders. Now, these guys, lymphocytes, T lymphocytes and the B lymphocytes, they are very specific for antigen shape. Very specifically check those specific shape and attack very selectively. That's why these guys are highly dependent on antigen structure. If they don't check antigen structure, then they are not activating. That's why these are kind of general defense, innate immune system. These are adaptive immune system, adaptive to the antigen structure. NK kind of in between, seems like NK belongs to here. Lineage-wise, NK is more similar to T cell, but they don't check antigen in the sense NK belongs maybe to this side. But there are kind of NK T cells. They have T cell receptor and also NK receptor. There's some mixed hybrid cells also exist. But for convenience, we divide the things. Now, CD. This is class of differentiation or class of designation. 99% of CDs are proteins, but sometimes there is lipid molecule, special lipid molecule, or power lipid molecules. They are selected as potential antigen for the antibody, and 371 has been developed to that. And these are adaptive immune system, means recognizing specific antigen. These are kind of unique immune systems. Just if there's something wrong, then just a few. So we have learned the first generation of chemotherapy. So this is the survival, this is the time. Usually when we treat the cancer patient, if they survive over 5 years, then the cancer drug is effective or fully cured. But over the time, chemotherapy is still the patient that die out. When we change that into signal targeting, targeted cancer therapy, that lifetime is a little extended. But eventually, there are also somehow the cancer is relapsed and expanded its lifespan, but still they die out. Now we are talking about the third generation, the immunotherapy. Now it seems like it's not perfect, but some patients they live quite long as a fully cured. Now with this, the observation, people believe that if we can combine some of these combination therapy, this is not to reach this expectation. We can cure much more percent and then they live much longer. So this is kind of the dream we have using this immunotherapy. So immunotherapy, somehow we use either immune cell or antibody. Everything can be classified as immunotherapy. Non-specific immune stimulation. If our immune system is boosted, then maybe it can kill cancer. So you have cancer, then they inject typhus bacteria into the patient, or E. coli, overdose. Then the cells are responding to the bacteria, and immunity is boosted. And maybe that boosted immune system may kill cancer. Sounds a little funny, but substantially ago, 100 years ago, that kind of trial was also tried, and sometimes it was a little effective. Cancer there, if we randomly boost our immune system, now sometimes it could cure the cancers. But now we hear if you overactivate our immune system, such as cytokine storm or autoimmune disease, kind of things also not talk. So there is kind of a non-specific cell transfer. We can give cells to the cancer patient. Any example? Can you think? When do you transfer cells to the cancer patient? After chemotherapy, before it was invented. or independently of the chemotherapy. After chemotherapy, what cell would you transfer? Yes, bone marrow transplantation is one way. If you have leukemia, then you remove all the other white blood cells and then transfer healthy donors, the bone marrow cells. Those are stem cells, hematopoietic stem cells. That kind of thing has been used. Or vaccination. Cancer may present antigens, but the antigen presentation efficiency is not too high. Then put in more antigen to boost those. It may be a little more sophisticated, rather than unrelevant the bacterial injection. We put more antigens, then boost those immune response. And it can be a little more specific. But these are a little the older version. Today we are going to talk two topics. One is antibody drug conjugate. B cell made antibody, but not only just antibody binding to that antibody, assuming that the antibody go to and bind to cancer cells, we put cancer drug on that antibody. That's ADC, antibody drug conjugate, which is the popular approach at the moment. Conceptually more the attractive and hot topic is a two topic. I couldn't get the second volunteer, so Taylor is going to present both of them, immune checkpoint and CAR-T. So to review quickly, so tumor microenvironment. Once the tumor is growing up, people say that our body, there are always a tumor is generated, something wrong, especially if you drink too much, smoke too much, there are always some cells get wrong. And if you don't treat them, they potentially can be cancer. But these cells are circulating, always remove them. Small cancers is easy to attack and clear out. But sometimes that first line defense fails, then they start to grow and colonize some chunk. Then that kind of immune system, that kind of a tumor chunk, there are cytotoxic T cells out there, CD8, CD4, and regulating T cells, NK T cells. All the cells are just getting together. But once they are becoming big size, then very aggressive attack may be too much. Then before the cancer dies, the whole body cannot sustain. It may kill host body first. Then the cells behave a little funny. Instead of very vigorously attacking those tumor, they tend to block those cancer. That is the police line. Don't cross here. If you don't cross, do not come out here, then I will help you. Kind of situation. So aggressively attacking macrophages we call M1. And those cells near to the cancer, they seemingly they are helping tumors. They were policemen before, and now it's not clear whether that's on our side or cancer side. They're helping tumors. Those kind of macrophages we call M2. So that's kind of a very strange situation. Once the first defense line is broken, and those environments around the tumor is not normal. It's something very chaotic, strange situations. That kind of environment we call tumor microenvironment. So there, cytotoxic T cells and NK cells attack the cells. If they don't have MHC, how do they do that? They check all the time. Okay. T cell first. Okay, MHC here. Now I check whether the antigen is there or not. If antigen matches, then I kill it. If they don't show the MHC, then now behind there, NK comes in. Okay, you don't have this ID, that you are not our citizen. You die. Kind of approach. So killer cell first. If they don't match, if they don't have MHC, then now NK comes in. And they are dead. So B cells, they make antibody. And the whole shape is this is 150K, and half over here, this is 1/3 over here, this is 50K, and this notch, this is single chain FTP size 25K. Okay, so the first topic is ADC. So let's invite Shinyu, and Shinyu will tell us about ADC. Welcome, Shinyu.
Shin-yo, and I'm going to present a presentation of antibody drug conjugate called ADC. This is our presentation of index. In history of ADC, in early ADC began in the 1950s and 1960s with the idea of combining antibodies and anti-cancer drugs. But however, these early studies did not have much success due to technical limitation and inefficient drug delivery methods. But in 1980s to 1990s, the advance in technology, DNA technology, mass production of antibodies became possible. So this period was particularly active in antibody research targeting cancer cells. Results such as Paul Ehrlich proposing the concept of a magic bullet. This magic bullet is we called ADC. And this is now clinical application. In this table, there is only 4 drugs ADC, but now there are 12 ADC, which is approved by FDA. There are compounds of ADC. First is monoclonal antibody. Second is cytotoxic payload and linker. Monoclonal antibody is this antibody. It binds to a specific antigen on the surface of cancer cells. And cytotoxic payload is this. It is drug which is used to fight the cancerous cells. And linker is this. The linker is binding agent between payload and antibody. There is the brief mechanism of ADC. First is binding. ADC binds to the antigen. And second step is internalization and drug release. Internalization of ADC followed by release of the cytotoxic drug inside the cancer cells. It can make cell die, resulting in apoptosis or bystander effect of the cancer cell. In target antigen, there is few key points of ADC. It needs to have high expression in tumor cells and low expression in healthy cells. For example, HER2 receptor, there is 100 times more highly expressed in tumor cell than healthy cell. And it should be displayed on the surface of the tumor cell to be available to the antibody. Finally, it should possess internalization properties to transport into the cell, which will in turn enhance the efficacy of the cytotoxic agent. And in antibody, there is 2 key points. First is target specificity. It should deliver the cytotoxic drug to the tumor cell. And second is target binding affinity. It should possess a high binding affinity to the tumor cell surface antigen. And third is cytotoxic payload. It can attack tumor cell by microtubule disrupting agent and DNA damaging agent. In our slide, there is DNA damaging agent and microtubule damaging disrupting agent. And finally, there is linker. There is non-cleavable linker and cleavable linker. Non-cleavable linker, it is degradation of the MAB compound in the lysosome, resulting in the release of a cytotoxic drug that kills tumor cells. In cleavable linker, it can acid-liable linker, lysosomal protease sensitive linker, beta-glucuronide linker, can cleavable linker, and next step is sent non-cleavable linker. There is some challenges and future directions. First is unavailable side effects. Antibodies are an awkward vehicle for transport, and it is difficult to navigate through the tumorous areas. Only 1% to 2% can transport it into tumor cells, so less than 99% can be inside in our body, so they cannot make side effects. And second is aggregation of ADC. It can occur at every stage as well as during transportation and long-term storage. And third is drug resistance of ADC. Drug resistance occurs when a treatment fails or becomes less effective, or when a tumor cell escapes. And there is limited antigen of tumor cells, thanks to this in our body.
In ADC, what is the role of antibody?
It can attach in tumor cell and can make payload, cytotoxic payload inside the tumor cell.
Okay, the role of antibody here is deliver the drug to the cancer. Unfortunately, still the yield is about only 1% can go to the cancer. 99% goes to a different place. It's not good enough yet. If that is true. Can you go to the picture of the grandpa? So now this contains the first page already. So this presentation, except the antibody with the drug conjugation, only picture is this grandpa. Okay, it contains quite a good amount of information there, but it's a presentation. It may be easier to use a different picture than those manipulating letters. So I got this presentation around noon time today, so I didn't have a chance to ask the senior to revise it. But it may be easier to get the eyes of the audience. Anyway, this person, Paul A, is a very famous person in terms of the inventor of the word, magic bullet. When he made that word, the magic bullet, it should go only to the target. But he meant small molecules. Small molecules may be circulating in our body, but only bind to the target protein. Then it could be magic bullet. Already he dreamed that kind of things, but that is quite difficult to achieve. Now it's almost distributed whole body, and then if it binds to the target, that may accumulate in the positions over the time. That's the best situation. Unless we have another controlling or really the molecule. Now, with the conjugation with antibody, it's also circulating through bloodstream. Through bloodstream to circulating, that antibody somehow should recognize something wrong place, penetrate, and then bind to tumor cell. How can they? Antibody size is 150 kilodalton. It's quite big. How they can easily penetrate the output from blood vessel? Small molecule may be much easier to penetrate. This is big macromolecule. How they can penetrate the out to the cancer cell? By protein interaction? That's one way, but if you use antibody, you may not use two different kinds of antibody. It's possible you can make a hetero antibody. So one side recognizing the penetrating part, the other side maybe binding to tumor cell. Maybe you can design the two, but if it's only one, okay, both sides have the same structure binding to the antigen on tumor, then you don't have other recognition part for penetrating part. In general, when the tumor grows up, they recruit blood vessels. Those blood vessels usually have very loose the blood vessel wall. So there are more of the non-specifically, but it's a little bigger holes. Bigger molecules even can easily penetrate into cancer area. So that's why that's a generally known fact. So that's why if you have some imaging probes, inject it, and see this binds to the cancer. Usually that can be severe because any molecules they can go to the cancer tissue. Any molecules can be swallowed by the macrophage. Okay? So whether that is really statistical or not, we need to check it. Okay, thank you, Jim. And one more question for Shinu's presentation. When he presented this ADC, what kind of a drug was used for coupling to antibody? He said something. There was a cytotoxic compound, for example. For example, what kind of cytotoxic? As we have learned here, microtubule disrupting or DNA damaging chemotherapies, cytotoxic compounds. Okay. So even though it uses the antibody, but if you look at the compound they use, that's belonging to first generation treatment. Antibodies that carry out those molecules to the cancer site. If it's non-cleavable, then antibody needs to be internalized and then digested in lysosome, and then that drug is released into the cell. If it's cleavable by some beta-glucuronidase or different enzymes near to the cancer is cleaved, and then only that drug is released and target the cancer cells. Action mechanism, first generation mechanism. Okay, not the second generation. Okay, so this is the concept of ADC. Sounds like just combining two techniques, but currently it's quite popular. Actually, under the research at the moment. So this ADC now. In this case, there is no the structural changes between an active binding. If you look at those antibody structure, where was the compound binding? Compound binding was around here. Right? So this is usually considered as a constant reason. Binding site is over here. Total size is 150, and those heavy chain size is this is 50. Right chain is 25. Binding every area is this is 25K. And what is the binding site on antibody? There is a two binding site, right? On antigen's binding site, what do you call? Epitope. And what is the binding site on antibody? There is a paratope. Okay, that one I wanted to remind you. Okay, so the interesting topic of this immune therapy, CAR-T and immune checkpoint. Now I invite Taeyoon for the second presentation. Okay, welcome Taeyoon.
Hello, my name is Taeyoon Kim, and I'm gonna introduce about immune checkpoint and CAR T-cell immunotherapy, which is
Here, here's the voice. Here I want to talk about immune CAR-T. This is a very bad study. Usually, if you hear the presenter's voice or his gesture, within 10 seconds you decide in your mind, I want to hear this talk, or I can be boring speaker. This is a bad habit. Take a little more seriously. I'm going to tell you quite interesting talk today. Your material is quite good. Then don't waste it.
Hello, my name is Taeyoon Kim, and I'm gonna introduce about immune checkpoint and CAR T-cell immunotherapy, which is classified as third-generation cancer therapy. These are my contacts for today's presentation, and first I'm gonna talk about immune checkpoint and immune checkpoint inhibitor drugs. The definition of immune checkpoints are molecules, protein molecules on certain immune cells, primarily T cells, that regulate the immune response, and they act as brakes of curves to prevent the immune system from attacking healthy cells in the body. So they could maintain self-tolerance and they could prevent autoimmune reactions when the immune system mistakenly attacks the body's own tissues. So, but in the case of cancer cells, they use this immune checkpoint system for their survival. In the case of cancer cells, they could express some molecules which could combine with a receptor which is expressed on T cell. So by this binding system, they could survive. So if we block this binding system, such as PD-L1 and PD-1 or CTLA-4, we could treat cancer cells more easily, and this treatment is called as immune checkpoint inhibitor drugs. The main target of immune checkpoint inhibitor drugs are PD-L1 or PD-1 or CTLA-4. And first, PD-1 is the receptor which is expressed on T cell surface, and it is related with a cell apoptosis. And PD-L1 is called as PD ligand 1, which is expressed on tumor cell surface. And if PD-L1 binds with PD-1, it could deactivate T cell, so they could survive. They could survive. So if we block PD-1 or PD-L1 by using anti-PD-L1 or anti-PD-1 such as nivolumab or atezolizumab, we could activate T cell and kill cancer cells well. And also CTLA-4 is a receptor which is expressed on surface of T cell, and if CTLA-4 binds with B7 protein which is expressed by APC cell, it could inactivate T cells function, so cancer cells could survive. So if we block CTLA-4 receptor by using anti-CTLA-4 antibodies such as ipilimumab, we could activate T cells, so we could kill tumor cell well. And these are the list of immune checkpoint inhibitor drugs which is allowed for treatment in Korea. And as you could see, all of these drugs are armed with MAB. So as we learned last lecture, they are all composed of monoclonal antibodies. But there are also side effects of immune checkpoint inhibitors. Immune-related adverse reactions such as autoimmune reactions in skin, stomach, endocrine, or liver could happen, and also the responsibility of immune checkpoint inhibitors are very low. So 2 to 4 out of 10 patients who respond to immune checkpoint inhibitors, but 6 to 8 patients do not respond. So we could use drugs combination to overcome limitation and side effects. And now I'm going to talk about CAR T cell therapy. CAR T cell therapy, short for chimeric antigen receptor T cell therapy, is a groundbreaking form of immunotherapy, and they involve genetically modifying a patient's own T cell, a type of immune cell to better recognize and attack cancer cells. And this is the process, a brief process for production of CAR T cell. And first, we have to collect leukocyte from patient's blood by using apheresis. And after, we will extract T cell from leukocyte. And by using viral vector, we could express CAR gene in T cell. Then, and the CAR gene will specifically react with targeted cancer cells. After proliferate CAR T cell, and we will treat these CAR T cell therapeutics to patients. And one of the most famous example of CAR T cell therapeutic is Kymriah. And it is directly targeted CD19 receptor, which is expressed on cancer cell. And by look at the figure A, CAR genes are composed of T cell activation domain and co-stimulatory domain. unhinged region and antibody rate recognition moiety, which is the fragment of antibody. And we will, by using viral vector, we will put these CAR gene into T cell, so we could make a CAR T cell. And this T cell could make a anti-CD19 CAR protein in case of Kymria. So by binding between anti-CD19 CAR protein and CD19 receptors of cancer cell, CAR T cell could recognize cancer cell more easily, so we could treat cancer more better. But there are also limitations of CAR T therapy. CAR T therapies are poorly effective against solid tumors, and also their targets are limited to surface antigen. So we have to more study for wide cancer therapy. Thank you for listening.
Great, much better. Okay, from this presentation, picture is quite good, picture correctly, and then those examples are given here in terms of very good summary, and it's quite interesting. Whenever you have a new topic to study, now this is open resources, ChatGPT. Even GPT 3.5, it is the 3.5 or 4.0. Okay, 3.5 is still much smarter than before, and they can do search to check the recent information. At least to have general idea, it can give you it can speak quite fluent. Language is not problem. So I wanted to know what is the new checkpoint, and that is a very good starting point. You can get idea within 3 minutes. Okay, if you use it, then that's stupid. Any new topic if you have to study, use it. Okay, this is good. The way to show the example. Moving down. So there is this kind of a checkpoint, PD1 and PDL1. So this finding, PD1 to PDL1, is this a killing signal or a saving signal? It's a saving signal. If I recognize it, then I save it. In case MHC sensing is a killing signal or saving signal? If you recognize it, it's a saving signal, right? If I don't recognize it, I kill you. Same situation there. If I recognize it, then you are one of our citizen. I don't kill you. If it is a blocked, either blocking ligand or receptor, it doesn't matter. Anyway, if they cannot meet, then I kill you. That's a new checkpoint. Okay. Checkpoint we learned in cell cycle checkpoint, whether I can go or not. That checkpoint was kinase, CDK, cyclically dependent kinase were checkpoint. Is that go signal or no go signal? Go signal or stop signal? Kinase. In cell cycle checkpoint, there was a checkpoint, the molecules are CDK, kind of kinase. Those kinase is a go signal or stop signal. It was a go signal. That's why we wanted to inhibit it, to block the cell proliferation. Okay. So in this case, this time the checkpoint only 20% or 40% works. That's why we want to find more checkpoint. May not be only this one. It's a first discovery. And then different type of checkpoint if we use as combination, maybe we can extend those coverage maybe 80%, 90%. Okay, so based on this good presentation in checkpoint and both of those concept. So the first part of the antibody generation part, you heard some of those names of antibody. So antibody at the beginning, we inject it when we make a monoclonal antibody. Traditionally, we injected those antigens into the mouse. The mouse generate the antibody, and we collect their B cells and make a hybridoma. We have studied that before, right? Make that live forever and let them make antibodies and select those cells and then make antibody. So this is a monoclonal antibody. In the beginning, those antibodies are mouse antibodies. Now, if you use this into the human body, problem is human recognize this FC part as antigen. One time used, the second time used, now they responded to this antibody. Then we cannot use it twice. That's why to try to make this into more human-like. So only FC part we use, and then this FC part and this part, human part, this is kind of a genetic one. And later even make it further. Most of those sequences they keep human structure, only those binding area, side. We change that into the mouse sequence over here. That's a humanized. Now eventually, just to put those the genes inside here, fully utilize the human cell as human antibody. So further and further we develop to do this infection. And those names, MAB, monoclonal antibody, blah blah blah, is antibody, monoclonal antibody. Now depending on those stage, this is a chimera, hema is chimeric antibody, and the humanized, most likely human, but still a little leftover mouse trait, tumor. And now we have a luma, kind of luma, so usually this is human antibodies. Now, CAR-T, chimeric antigen receptor. So in T cells are the case, this is CD8 cell partner MHC1, helper cells partner MHC2. So usually we heard that the organ transplantation is rejection. Those rejection happens because of this MHC. We have some sets of MHC, and then it's delivered from one part from father, one part from mother. Even between siblings, sometimes it doesn't match. That's why this is the main problem for the organ transplantation. So if you look at the structure, this is the T cell part. They have a T cell receptor. And then this is antigen presenting cell. It can be macrophage or B cells or any cell types like the cancers. They needed to carry this MHC1. If not, they are attacked by NKs. The NK is circulating. They don't check antigen. They just check this antigen presenting part. So when they bind T cell, they have one CD8, CD4. These are functional proteins. CD8 recognize MHC1. CD4 recognize MHC2. So this is one side recognize, okay, now I find MHC, now I use the T cell receptor and check those antigens. So two sides, they need use it together. So that's why if they don't have MHC, T cell receptor doesn't work. Because it has two hands they need. When antigen is a small fragment, but is presented here, then if you look at the structure a little more for the T cell receptor, so this is a T cell receptor side, and this is a partner cell, either cancer or antigen presenting cell. Then they present this through MHC. There is another the protein, either CD8 or CD4 recognize this part, and this part. If you look at T cell receptor. How does the T cell receptor recognize a different antigen? It looks very familiar, very similar to what? Antibodies. Antibody has this kind of a recombination to make different particles. The T cells, they have exactly the same system. Both CD4 and CD8 cells. So in our body, we have an antibody generating library, T cell generating library. The function is almost similar. They have this kind of recombination, maturation, kind of things ongoing. So usually they don't explain that if you don't know immunology seriously. Just by looking at this picture, okay, this is paraport-like structure. T cell receptor has a lot of different combinations. And this one needs to bind the MHC, and then they can recognize. That's why if it's a small invader like a bacteria, antibody is more efficient. Antibody size is quite big. Bacteria this size, this antibody can bind. Several of them bind, and then maybe we can kill. We can block the function. Cancer cell too big. So that's why antibodies function may be less important. It's more important to maybe using T killer. Come in and they recognize, okay, you are the enemy. Then I inject chemical weapons. Okay. That's why for cancers, the killer cells function is kind of very important, and the recognition part is like that. Now, problem is, now this is a two-hand approach. If this cancer somehow they change MHC binding site recognition or any part of here, they can evade, they can escape from this binding possibly. So, or in case the T cell receptor diversity may not be good enough, then even though there is in case, it is. Now let's say originally this was a T cell receptor. Now it may not bind to the antigen efficiently enough. Then to reboost those recognition parts, one strategy is why don't we change this into antibody fragment? Those antibody fragment, which is they use, this is antibody 150K, and this part, this is antigen recognition part after research. To make it easy, connect this, originally this is a two peptide chain, but connect this into one, so this is a single chain. That is easy to express. And select this part and then put that into T cell. Then this T cell originally it recognizes the antigen by MHC recognition part and the T cell receptor. There is their own function. So even though it doesn't work, now they have separate independent binding motif. And this binding motif does not require MHC. This is like antibody, just recognize directly the antigen site. So even the original binding event does not work, now this is a new function there. And for those downstream, they try to make it generating more cytotoxic response, bind it and cytotoxic. And also bind, then maybe proliferate better, make more cells. And it can live long. Or if it go too long, then maybe there is another switch. If you want to, you can stop the function of the T cells. Kind of the development is ongoing for this. This is a CAR T. Chimeric antigen receptor means this is chimeric antigen. It's not original T cell receptor. This is originally B cells, the recognition part, fragment of antibody. There is a effective on T cell. And utilizing T cells' original function of killing cytotoxic weapons together and go. Then, if you hear CAR NK, what do you think? Make an NK cell. Originally, NK cell is a innate immune cell. It's not adaptive. But if you hear CAR NK, that means you added this fragment onto the NK. Then it's not generic killers. Now it's a specific killer for the target, which is possible. So that kind of thing is expanded. CAR macrophage, CAR dendritic cells, right? So that concept is spreading out now. CAR T is just the first example introduced. Okay. So using this, now this as the single cell, single chain FB, they can recognize the antigen site and induce the killing of the cells. There was a drama, maybe it was a publicity. Have you seen? So the heroin, the blood tumor, something spread out the tumor in the brain, and she went to Germany to get the CAR T therapy. It doesn't work for very well for solid tumor. It's a spread out tumor. It's a perfect model for CAR T therapy. So even to understand the drama of the story, CAR T is important. Okay, so for this CAR T, and already tell the talk, to do that the experiment, you need to get your own T cells. Means your immune cell is at least have some functions. You need to have enough numbers of the white blood cells. Collect them, and then modify, and then adding those cytotoxic motifs and multiply, make more numbers of cells. So for those, he mentioned mentioned, a process is collecting those and then centrifuge. Then upper part is the plasma, bottom part is the red blood cell, and this part, the purple part, is the white blood cells. So you discard this, you write this one, and among them, and then use it. Now this term, plasma versus serum. I was always confused which means plasma and serum. Hey, Daniel, what is the difference between plasma and serum? See, this is my English problem. This is the scientific technology terms. Hey, what is the difference between them? Okay, if you take the blood and then spin down those blood cells, then everything floating around on top, those are, in the beginning, this is the plasma. From plasma, if you remove blood aggregating factors, the clotting factors, then that becomes serum. So always I was a bit confused. So this is plasma, this is serum. So I tried to memorize primary, secondary. Primary, if you take the best plasma, contains more proteins. If you are not careful, then they can aggregate. So removing the part, cleaner version is a serum. It contains the antibody in here, but it does not have aggregation part. Chong is a cleaner than Jang, so cleaner is a serum. That's how I remember it. So to do that, if you just take one blood and spin down, that's only batch to batch. So sometimes we need a lot. Then this kind of a circulation system. Take a blood and then centrifuge continuously, and then this is going back to the bloodstream. The plasma goes back to the body, and then this one accumulates further. Then that's a body code, including different the blood cells. And those blood cells, it has B cells, macrophage, non-macrophage, monocyte, precursor of macrophage, and NK cells, others. You need to purify the T cells. How to purify T cells? Using the technique what we have learned so far. How can you purify only one type of cells? We didn't learn it. We didn't learn flow cytometry. We learned the flow cytometry. Did we learn facts? Okay, flow cytometry, you add flow cytometry, you add a fluorescently labeled antibody, and then we can see, okay, by the fluorescent signal, by changing those voltage, you can physically separate out. So to do that, T cell enrichment, you can add CD4 or CD8 antibody, and then fluorescent label, and you can see, okay, this is CD8 population, we can collect it. Problem here is, those molecules are functional molecules. CD8, CD4 is not just showing the identity, it's a functional molecule which binds to the MHC. If you add antibody to those functional molecules, it can change the property of the cells. So if possible, you don't want to touch your positive cells. In this case, positive cell is the CD8 cell, killer cells. One possibility in this case is you use magnetic field using the antibody, and these antibodies binding to all non-T CD8 cells. It's a mixture of antibody binding to T cells, CD4 cells, monocytes, and they bind to those cells in this magnetic field. And through this magnetic bar, then if it's not bound, if it's very bound, then they just stop here. Non-bound cell passes through. CD8 cell can be collected negatively. Antibody did not bind to CD8, so CD8 killer cell is safe. This is kind of a negative 13, and previous one was fluorescence activated cells of the FAX. Now this is magnetic activated cells of MAX. If you hear negative MAX, that means only stay with your target cell untouched. All other cells you remove by magnetic field. Right? Yes. Through this method, you can correct the CD8 cell. And then you can modify gene modification. That means introduce the single cell, the FB, the 60 gene inside here. Let them make something new. And okay. So this is the target. more general question. In TME, tumor microenvironment, why do we need immunosuppressive cells in disease? Because if it's too aggressive, then it kills your body first. So that's why in these situations there are M1 and M2 live together. So most likely, if it's well-developed tumor, there may be more M2 than M1. It's a mixture, but population-wise, this is higher. So they interfere. Other killer cells don't kill it. I can control it. That kind of situation. So using this situation, there is a one modern approach of cancer treatment is changing the cell fate from N2 to N1. They are differentiated. We learned about differentiate the cell, can go to the stem cell, can go back. Then maybe go up a little, and then go to the N1. It's both of them is differentiated. If they go up, then they end zero, like a monocyte state. And then go up and move here. Then they are already new to the cancer. Right? Delivery is no problem. Those cells are already in cancer area. And if they change their mind, they attack. And that's quite efficient way. So they are trying to develop this kind of drug, which can change the fate of N2 into N1. Then can kill cancers. Another approach. Sometimes we have autoimmune disease. Rheumatoid arthritis. For me, not yet. Hopefully not forever. But if you have that kind of a M1 aggressively already here, it affects our body. Then you put those drugs. Those drugs function, changing the N1 into N2. Then you have curing of autoimmune disease. Okay? So then we need to understand what is the rationale behind. Our body has always those balance between progressive attacking versus suppressing. The balance is quite important. And sometimes we need to boost this, sometimes we want to boost this. Okay. So this is the end of the immunotherapy. Today we have the two friends, the presentation. Next week we are moving to aging. And Imran is going to make a small presentation for that aging and anti-aging and in connection to